Hello, I'm Ed Wicklein with Crollo Engineers, here today to talk more about the technical guidance manual and computational fluid dynamics modeling of chlorine contact basins that we've been developing with the Colorado Department of Health and Environment. Today, we're going to talk about the CFD model setup and simulation, Module 5. Hopefully you've had a chance to review the other modules. The last one was developing the geometry and the computational mesh. So we have our computational mesh that is ready to be read into the solver. On our flow chart, we've built the mesh, we have a quality mesh, so now we're at the point where we set up the model. We'll solve it, verify convergence, and then run through a quick mesh independent study to make sure we've resolved the geometry sufficiently to generate a quality solution before we move on to simulating our actual test conditions and determining the contact basin baffle factor. So we're going to open Fluent, make sure we're in double precision. Other solvers have similar startup procedures, make sure we're in 3 dimensions. We'll open the model or open the software. Read our mesh that we wrote out in the last step. In the console window, you get some information. Again, most of the softwares are similar, provide information, summary, other parts of the model. There's tools here that you can do mesh checking. We will need to scale it. If you recall, we set up the model in feet, but Fluent, in this case, defaults to meters, and so we'll want to scale our mesh so that we're in the appropriate units. You can use features like changing the view units if you'd like. After we've read the mesh one, there's a few other parameters we can set here. It's going to be a steady state solution, and we don't need to activate gravity as there are no density effects that we would expect in this particular problem. We need to set our turbulence model. In this case, we've picked the K-epsilon realizable model as a base level model. It's a good 2-equation model that we've gotten good results with on a number of studies when we've compared back to various types of field data. After we pick that, we need to set our fluids. And in this software, it defaults to air. We obviously are not simulating air. And if we look at the model, it brings in the density and the viscosity for standard conditions, approximately 20 degrees Celsius, which is what we'll be simulating today. But if we were going to be simulating a different temperature, we would need to adjust the density and the viscosity here accordingly. We're going to set up a second fluid that'll be our tracer, which is the same properties as water. Just make this tracer, which we'll use later in our simulation, so we don't have to come back to this step. So now we've set up our simulation models, our materials, make sure that our fluid domain is water. And next it's time to set our boundary conditions. We've got a number of options here. We've got our walls, which would be the internal baffles. In this case, because they're 2D, they're two-sided. So the fluid cells on each side would see it as an outside wall. We've got our surface. And this would be set to a zero shear wall so that there's no effective roughness on it. The other walls will use a default wall roughness, just based on the turbulence model with the default parameters. We have an outlet. In this case, it's just there's one inlet, one outlet, so 100% or a factor of 1 of all flow coming in goes out that outlet. And we need to set the inlet, which there's a couple ways to do this. We're going to use the velocity magnitude normal to the boundary coming into the domain. So it is helpful to have a spreadsheet set up for yourself to track the model. We're setting up for 4.5 MGD, which translates to a flow rate that we'll have to input, or a velocity that gets input to the model. And so the inlet area is 1.77 feet, which translates to a velocity of 3.94 feet per second, but of course we're set up in meters, so it's 1.2 meters per second. So 1.2 meters per second, and we do want to specify some turbulence parameters, intensity and hydraulic diameter easiest. They can be calculated from a couple equations that you'll find in your specific software's guidance documents. The hydraulic diameters 0.457 meters, and the turbulent intensity based on the Reynolds number is 3.1%. So that's our boundary. And we need to go through and set up our solution methods. We use a simple scheme. There's a number of velocity pressure coupling schemes available. We'll use Presto for pressure, and we'll leave the minimum at second order. We'll convert all these to second order accurate schemes. There are higher order schemes available as well. The given software's manual will have more information on that. Solution controls. We'll leave you under relaxation as is. We do need to set up some monitors. There's the global residual, which is under ultimately report plots. So we've got an absolute criteria of 0.001 for everything for now. And we'd also like to define some point monitors at areas of interest. And so we would set up our points here. These are in wake regions at some of the bends that we've pre-estimated as areas of interest. And so for XYZ coordinates, so we create a point, these locations. Got a monitor point, we'll want to plot it. We need to define it, new surface report. So we can pick finite vertex average for a point, can monitor pressure or other parameters for calculating what the velocity magnitude. Pick our monitor location we just defined. The solution needs to be initialized. There's different options to initialize it, but it's solved iteratively, so it needs some values initially assigned to the matrices for the, to start solving from. And different softwares have different requirements, again, or sensitivities. So you need to know your software. With Fluent, starting with zero velocity is okay. With other software, it won't start with a zero velocity. It'll need a small value. Initialize the solution. If you have calculation activities, you set them here. We go to run solution, set a representative number of iterations, and we would start calculating our problem. It's a good idea to save it before this point, but we're just going to take a quick sample of how it runs. On this particular machine, it's probably a little bit large, so it's going to take a minute to start going. And as it iterates, it provides information on velocity residual, continuity, turbulence parameters. Let's see how long each iteration is taking, the time step. Different solvers will provide different information. And we missed a step, so we'll go back. We defined our monitor point, but we forgot to tell it to plot. All right. And then we'll continue running. And so it's tracking the residual here, each iteration, how it's hopefully decaying or converging on a value. Take another look. Our monitor's not plotting correctly. So then the solution runs, and it'll take between a matter of minutes and several hours to solve, depending on the computer you have. And so rather than going through the process, we have pulled some of the output to take a quick look at. So we've set it up, and our convergence curve on an example would show continuity in this case, rising and falling depending on the initialization, everything's big. Most of the values here are less than 0.001. The continuity is a little bit unstable in this case, and it's converged slightly above where we normally like it, but it's not changing. We're also monitoring the velocity at points as we set up, and we can see that at this point, there's some fluctuation, and eventually the velocity stabilizes. The other monitor point we set up, it stabilized much quicker. And if we look at these results, the residual is not changing, the velocity is not changing, and so we would define this as having a converged velocity solution at this point. Now we need to do a mesh independence check following this. And so for this case, we looked at an area where there's some amount of instability in this wake region, flows coming down this channel, makes the bend. There's a non-uniform distribution here. So we set up a uniform grid of points where we extract the velocity data at all of these points, plotted on a one-to-one curve. So we've done that between 3 levels of mesh refinement. We have a coarser mesh with less cells across the width, a medium level mesh with more cells, and then a fairly fine mesh. We're trying to establish what level of cell size we need to resolve the particular problem. Every problem is going to be a little bit different. And so comparing the coarse, medium, and fine at these locations that are grid independent, it's just a uniform set of points within the domain. When we plot them, we see that the coarse to medium comparison, there's quite a bit of scatter across the one-to-one line with an R squared of 0.95. So even with that scatter, it's pretty good. When we look at the medium to fine comparison, we've got an R squared of 0.98. They're much more closely matched. And so we would conclude that we probably have a mesh independent solution here at the medium level. With that, I'll be happy to answer questions via email, or we'll be having a live session in a few days that will then be recorded with questions. Following this, we are now verified mesh independence. We're ready to run our flow conditions. And so we would start with this model and update it for that.